You probably already know that weird stuff happens in the realm of special relativity as you start moving with really high velocities. Hold on, I hear you cry. Surely a mass of 1 kilogram is a mass of 1 kilogram. It doesn't matter how fast it's going. But as with all things physics, this is just another approximation, and the 1 kilogram mass really does gain mass as its velocity increases, although of course it depends who's watching. The Lorentz factor, also known as the gamma factor, is an expression that tells us what happens to things like mass or energy or length or even time as an object moves faster. The formula for the Lorentz factor looks simple enough, but it's a tricky one to use. You can put the values in 2, 3 or even 4 times and get 2, 3, 4 different answers out. The Lorentz factor appears in several formulas such as these for mass or energy or length or time. As you can see, these formulas are really similar to each other. Let's take an example of how this plays out in air quotes real life. Let's consider how the mass changes as it moves fast, and as we saw earlier, this takes the formula of m equals gamma, or the Lorentz factor, times m0. And m0 or t0 or L0 is defined as being the proper mass or time or length. But what the heck is the proper mass? Well, the proper mass is measured in a frame of reference that is stationary compared to where the events are happening. So you might think, well, stationary, you might think, well, that's me standing in the lab, I'm stationary. No, you're not. The Earth is moving. So proper mass is measured in the frame that is stationary to the mass itself. In other words, to measure proper mass, imagine yourself sitting on the 1 kilogram, zooming along with a pair of scales in your hand, measuring the mass of that 1 kilogram. This chart attempts to show how the Lorentz factor changes with velocity. You can see that I've expressed velocity in meters per second, but also as a percentage of the speed of light in the middle column. When the velocity is small, like 10 meters per second, you can see that as a percentage it's basically 0, and so the Lorentz factor is 1. It's not 1, but it's as near as makes no odds. You can say a similar thing really with speeds like 500 meters per second and even 10,000 meters per second. The Lorentz factor is basically 1. Even when you get to, sarcasm alert, vanishingly small speeds like 1,000,000 meters per second, the percentage of the speed of light is still only 0.3, meaning the Lorentz factor again is basically 1. It's generally accepted that the Lorentz factor only really becomes relevant when you get to speeds that are around about 10% of the speed of light, and even then it's only 1.005. As you keep increasing the velocity and bring the percentage closer and closer to 100, you can see the Lorentz factor starts shooting up. What would the Lorentz factor be for an object that is actually moving at the speed of light, do you think? Imagine moving our 1 kilogram mass at a massive speed of 30 million meters per second. This is 10% at the speed of light, meaning the Lorentz factor is 1.005. This means that the mass seen by the observer, m, is actually going to be 1 times 1.005 or 1.005 kilograms. As you zoom along with the 1 kilogram bowl of sugar sitting on the scales, to you, the mass will stay as 1 kilogram. That's why it's called the proper mass. Now let's speed up the bowl of sugar with you carrying it to 99.667% the speed of light. The Lorentz factor is now 12.258, meaning that to you, the mass still is 1 kilogram, but to the observer, from whom you are moving away at 99.667%, the mass they see is 12.258 kilograms. So I hope you can see that the Lorentz factor is actually pretty straightforward once you know what you're doing with it. And it's also really cool and helps you get an understanding of what's going on in special relativity. Do let me know what you think in the comments below.